Good day, everyone. Welcome to lecture number 29 of Theory of Computation. And in this particular lecture, we will be discussing about the designing of Turing machines. So in our lecture number 28, we started the discussion about the Turing machines. We got the idea what are Turing machines. And we know that, let me recap it a little bit. So Turing machines, they have a finite control, okay, or we can say they have finite states, and they have an unbounded memory. Okay, so this is the unbounded memory. Fine, and the tape head is attached to this unbounded memory, and this tape head can move in both the directions, left direction or right direction. And every transition in a Turing machine, so there is a transition from a state on an input alphabet, and it goes to a new state, Q dash. It writes a new symbol at that location, and then it moves in the left or right direction. Fine. So today in this particular lecture, we will be designing some Turing machines. We will be giving examples for different languages, and we will design the Turing machines for those languages. And that will help us to understand how we can design Turing machines for different classes of languages. So let me start the first example related to designing Turing. So let's consider this particular language. L is equal to 0 raised power n, 1 raised power n. We know that this language is a context-free language. We already know it. So our aim here is to design a Turing machine for L. What does that mean? We mean to say that we have to design a Turing machine that will accept only those strings that are of this format. This format means that they should start with 0, okay, end with 1, and number of zeros should be equal to number of ones. But first there should be only zeros, then there should be only ones. Okay. So we have to design a Turing machine for this. So let's write our solution, or we can say let's design a Turing machine. See, for designing a Turing machine, the first part is that we are given an input. So input is given. So what will be an input? The input will be a string. Okay. And for this string, we have to design a Turing machine such that if this particular string belongs to this language L, so what I am saying, if this string S, if S belongs to L, then our Turing machine should accept S. Accept S. Else it should reject S. Okay. So this is the complete procedure that we have to follow, that we have to make a Turing machine such that it will accept only those strings that belong to this language. So if we are given a string, so this is our string. The first job is to see whether this string is of this format. So first thing that we will check is check whether S is in the correct structure. Correct structure means that in the S, first we should have zeros, okay, then we should have ones. So first part is we should check this structure. Okay. So in this part, if S has a required structure. Required structure means that if S is in this particular format, in this format, okay, then we have to check whether the number of zeros is equal to number of ones. So if it is in format, if S has a required structure, then check number of zeros is equal to number of ones. Okay. Else means that S does not have a required structure. That means it is not in this structured format. So it by default means that reject S. Okay. We have to reject S. We will see how we will check whether the number of zeros is equal to number of ones. We will check that thing. But first part is we have to check this structure. Okay. So let's see how we can check this structure. But you have to remember that we have to check the structure using the Turing machine, the Turing machine that we are designing. So the first part of this problem is, part A is check structure of S. Okay. So if this S passes in this part 1, then only we will move to part B. So what is the part B? The part B will be check number of zeros is equal to number of ones. So if our string S passes in both the parts, in part A and part B, then only we will say that S has been accepted. So we will write if S passes part A and part B, if S passes part A and part B, then S will be accepted. Else S is rejected. Okay. So we have to design a Turing machine for part A and for part B. So first is part A, check structure of S. So let's see what we have to do for part A. So what we are going to do, we will first start in the initial state, Q0. So let's say it is the initial start. Then in this state, this initial state, this is our initial state. Initial state. Okay. So in this state, we will remain in the state till zeros are there. Zeros are there. Okay. So if this is our Q0, state Q0, this is our starting state. So what should be initially? Initially, there should be only zeros. So initially, whatever input is there. So if it is 0, so we will write 0 there. We won't change the input alphabet and we will move right. Right means check next symbol. Okay. So we are going to check the zeros. However, in this Q0, if 1 comes, it means that I have checked zeros. Zeros have been checked. Now there are ones. Okay. So that means if 1 comes, I will go to a new state, Q1 state. Okay. So if 1 comes, I will write 1 and okay. So that means if 1 comes, what should be there? There should be only ones. Okay. There should be only ones. So I will remain in this state. So whatever 1 is coming, I will rewrite 1 and R. However, if 0 comes here, so that means I am not in the correct format because I have seen 1 and then there are zeros. So that means it is not in the actual structure. What was the actual structure? First we should have zeros, then we should have ones. So that means in this Q1, if 0 comes, I will write 0 and I can move in any direction, left or right, but I will go to a reject state. Q reject. Reject means that my string has not passed the part A. So if it has not passed the part A, that means the string will be rejected. Now, if the case is like this, we have zeros and then we have ones, and then there comes a blank. Blank means that string has completed. So that means if blank has come here, blank has come, I will rewrite blank. I won't change anything and I will move left. So that means I was here. Now I am here. So now I am in this state, Q2 state. So what is Q2 state? Q2 state means I have checked the structure. So if I have reached to Q2 state, so that means my string has passed part A. Part A. So that means it has the correct structure. Correct structure means that first there were only zeros, then there were only ones. Now I am in state Q2, in this state, okay, Q2 state. Now part A is completed. Now I have to start part B, okay. But for starting part B, currently my head is here at the end. I should move this head to the initial point. Then only I will start the part B. So from Q2, what I am going to do, I will move to the left. Okay. Move to the left, whatever is coming. So if 0, 1 is there, I will rewrite it as 1 and move left. If 0 is there, I will rewrite 0 and move left. So I am moving left. Now I am moving left after reaching here. After there is a blank. So that means in Q2, if blank is there, so that means I have moved to the initial place. I have to only move one place to the right. So that means here at Q2, if blank is there, I will rewrite blank and I will move one place right, this position. So now I am in the initial position. Okay. So let's suppose I am in state Q3. So now I am in state Q3. Now I have to do the part B. Okay. So let me make this diagram in clean format. So what is the part A? Part A is check the structure. And what is the actual string? This is Q0. This is the initial state. So on Q0, if 0 is coming, we will rewrite 0 and move right. If 1 is coming, I will rewrite 1 and move right, then move to state Q2, Q1, sorry. So here I am checking ones so that there will be only ones. I will rewrite 1 and move right. However, if 0 comes at this point, if 0 comes, I will rewrite 0 and I can move in any direction, left or right, but I will go to a reject state, Q reject. Okay. And however, if blank is coming here, blank means the structure is in the correct format. I will move left. So this is my state Q3. what was the name? State Q2, sorry. State Q2. Now Q2, that means I have completed the structure. Now I should move to the initial point of the string. So this is how we will move to the initial point. Okay, and if blank is coming, I will rewrite blank and I will move one position to the right, and now I am in state Q3. Okay, so this was the part A. Now we have part B. What is part B? Part B is check number of zeros is equal to number of ones. So we are currently in state Q3. So what was the aim of this part of the Turing machine? So this part of the Turing machine, what is its aim? This part. So the aim of this part is check structure of a string. So if the structure is not in the correct format, then we will reach to a reject state. So the Turing machine will reach to a reject state and it will reject the string. However, if the structure is correct, then we will be in state Q3. And now we are in state Q3. Q3 means that part A has been checked. Our string has passed the part A. Now we have to check whether it will pass the part B. Okay, so how we are going to check? So what is the idea? The first part is what we are going to do. So can anyone say here, how will we check whether the number of zeros is equal to number of ones? So this is our input tape. Okay, so these are our, let's suppose, zeros, and then we have ones. So we have zeros, then we have ones. Okay, so our input tape head is here. Okay. So how will we check? What we are going to do, we will first check this. If this is 0, okay, we will remove it. Okay, so we will remove it. Remove means place the blank. Okay, then corresponding to this 0, we will go to the end of the string, and at the end we will check if there is 1. If there is 1, we will replace it with blank. Then again we will come to the initial point. Initial point means this one. So this one has been a blank. We have replaced it with blank. So now we will go here. Again 0 is here. We will replace it with blank. We will go to the end. So end is here because here we have blank. We have replaced it. Now end is here. So we will replace it with blank because 1 is there. Again we will come here. Okay, we will replace 0 with blank. Again we will go to the end here. So here we have 1. We will replace it with blank. Again we will come to the initial position, that is here. We will replace with 0 with blank. Again we will go to the end. Now end is here only. Okay, so that means this 0, after removing this 0, we are not able to find the 1. Okay, so what does it actually mean? What we are doing here? We are the first step is rewrite 0 with blank. Okay. Second is go to end and rewrite. Go to end and rewrite and find 1 at the end and rewrite it with blank. Third, go back to home. Go back to home. Home means at the initial. Go back to home. Fourth, repeat 1, 2, and 3 till there is only blank symbols. Okay, fine. So this is the procedure. So if we are able to do it, then that means number of zeros is equal to number of ones. So let me make a complete picture here. So basically we are in Q3. Okay, so Q3 means we have completed the structure, checking the structure. Okay, so let's say Q3 is our home. So what we are doing at the home, when we are at the home, so our Q3 is home. So at the home, what we are doing, we are checking if it is, so what we are doing here, if it is 0, we will rewrite it with blank, okay, and move right, one position right. Then what we have to do, we have to go to end. Go to end. So how we are going to the end? So we are going to the end. If it is 0, we will replace it with 0 and go right. If it is 1, we will replace it with 1 and go right. So we are trying to go to the end of the string. So that means we are moving one place right again and again. Up to which point? Up to that point till we reach the last of the symbol. So last of the symbol will be like this. So if we have this, so let's suppose we have like this, 1, 1, and after that we have blank. So we are moving one place to the right each time. So move right, move right, move right, move right. Now we have reached to a blank. Blank means that we have gone to the extreme right. So if I have seen blank, okay, blank, I should replace it with blank and move left. So that means now I am here at this point. At this point means I am at the end. Okay, so I have reached to the end. So when I have reached to the end, what we are going to the end? Go to the end and find 1 at the end. So we have to, if there is 1, so this is our end. So if there is 1, what we have to do? Find 1 and rewrite it with blank. Okay, so if there is 1, we will rewrite it with blank. Okay, and what we will do? We will move left. And after that, what we have to do? We have to, so let me see here. So we have to go back to home. So here we have to go back to home. So how we will go home? So we will move one place to the left till we reach a blank space. Okay, till we reach here. So that means if 1 is there, we will rewrite it with 1 and move left. If 0 is there, we will move one place to the we will move to the 0 and we will go to the left. And now if blank comes, that means we have reached to the end. Now we have to move one place here. That means we are at the home. So that means if blank is there, so let me write here. If blank is there, we will replace it with blank and move one place right. So we have reached to the home. Now at the home. So now let's suppose we are at the home. So let's see, this was the home. And now let's say if at the home there is blank. Blank means that everything has been completed. Okay, so that means there is nothing left. Blank means that all the cells are blank. Okay, so that means if I am at the home and at the home there is blank. Blank. So what I am going to do, blank, and then I can move in any direction. And that means I have for each zero, there is corresponding one. So that means number of zeros is equal to number of ones. So in that case, we will go to a state Q except. Okay, fine. So this is our Turing machine. And we know while designing a Turing machine, we said that all missing transitions lead to reject state. So what are the missing transitions here? So you can see, so here on this, we have transition on 0, 1 and blank. So here at this end, at home, we have transition on 0, we have transition on blank, and there is no transition on 1. So if there is no transition on 1, so that means if 1 comes, we will replace it with 1 and we can move in any direction and will go to the Q reject. So here all the transitions are done. Here also all the transitions are done. Here there is a transition on 1, but there is no transition on blank and no transition on 0. So for those two transitions, for blank, we will replace with blank and go in any direction. For 0, we will replace with 0 and any direction. So it will go to a reject. Go back to home, we have transition on 1, transition on 0 and transition on blank. So this is our Turing machine. So this part of the Turing machine, it determines number of zeros is equal to number of ones. So if number of zeros is equal to number of ones, we will end into the Q except state. However, if the number of zeros is equal to not equal to number of ones, we will go and stuck in the Q reject state. Okay, so this was the complete Turing machine for determining the number of ones is equal to number of zeros. So let me make it the complete, the first two parts and this part. So let me stop this and let me first complete this. So this is the complete, we will say the Turing machine for L is equal to 0 raised power n, 1 raised power n. So this Turing machine will accept only those strings that belong to this language. And the strings that does not belong to this particular language, they will end up in this Q rejected state. So this part of the Turing machine, this part, this part of the Turing machine is for checking, this part checks structure of a string. And this part of the string, so So the other part, so this part of the string, sorry, this part of the Turing machine. This complete part. So this part of the Turing machine is check number of zeros is equal to number of ones. Okay, so we can say that this Turing machine has two parts. So the first part of Turing machine, so this part, it is for checking structure of string. Okay, and this part is combined with the another part, and the main functionality of that part is to check number of zeros is equal to number of ones. So this is our complete Turing machine. So we can say that this part is also a Turing machine. So this is Turing machine 1 and this is Turing machine 2. And we have combined these two Turing machines to design a Turing machine for L is equal to 0 raised power n, 1 raised power n. Okay. So we can say here, you can check here that each Turing machine can act as a subroutine. Okay. So what is a subroutine? Subroutine means a function. Okay. We know that in programming languages, why we require functions. A function is required so that if, let's suppose we have a function to add two numbers, instead of writing the code again and again for adding two numbers, we can use that particular function repeatedly. So likewise, if I have a Turing machine, let's say that Turing machine is doing some job. Let's say it is doing job 1. Okay, so this is Turing machine 1 doing some job 1. Now I have some another Turing machine that has multiple jobs. So let's suppose it has to complete job 1, job 2, and job 3. Instead of designing a new structure or new Turing machine for job 1, I can use this Turing machine 1. So I can use Turing machine 1 to perform job 1. Then I can take its result, give it to another Turing machine that is performing job 2, and then the result from this Turing machine can be put to Turing machine 3 that performs job 3. So these three together can perform job 1, 2, and 3. So that means these three Turing machines can be combined to design a larger Turing machine that is able to do these three jobs together. Okay. So we can say that each Turing machine can be used as a subroutine for solving some other problems. Okay. So we will discuss some more problems and that will give us the clear picture how Turing machines can be used as a subroutines. So let me wrap this portion here and now let's discuss another problem and we will design a Turing machine for that problem as well. So let me wrap this and we will discuss another problem. So let's take another example. For example, let's say L is equal to W belongs to 0, 1 star such that W has equal number of zeros and ones. Okay. So this is our language. So we have to design Turing machine for L. So what was the difference between the previous one? The previous was L is equal to 0 raised power n, 1 raised power n. So here also we have equal number of zeros and ones. So what is the difference between this L and this L? So in this one, so we should have first zeros and then we should have ones. Okay, and number of zeros should be equal to number of ones. But here there is no such restriction in this L. So there is no restriction on the structure. On the structure. So the number of, so the zeros and ones, they can be any order. For example, 1, 1, 0, 0, 1, 0. Okay. So let's name this L1 and let's name this L. So 1, 1, 0, 0, 1, 0. So in this, number of ones and zeros are equal. So this string belongs to L1. But this string does not belong to L. Why? Here, number of ones is equal to number of zeros, but the structure is not like this. So what is the structure? First, we should have zeros, then we should have ones. So I hope that you understood the difference between L1 and L. So the difference is only in the structure. So in L1, there is no restriction on the structure. Okay. So when we are designing a Turing machine for L1, okay, so when we are designing a Turing machine for L, we designed two Turing machines, Turing machine 1 and Turing machine 2. So this one was finding out the structure. This one was for the structure. And this one was for determining the number of zeros is equal to number of ones. Okay. But in this scenario, we have to design a Turing machine, but we know that there is no restriction on the structure. So that means there is no need of TM1. No need of Turing machine 1. Why? Because there is no need of a Turing machine. It is because we don't need to check the structure, because the structure can be anything. We have to only see the number of zeros should be equal to number of ones. Okay. Now the second is, can we directly use TM2 for L1? So this is the question that we have to answer. Can we directly use TM2 for L1? So what was the job of TM2? So Turing machine 2 was finding the number of zeros is equal to number of ones. Can we use the same for this L1? Let's see. Can we use it? Okay. So what was this Turing machine doing? So this was the Turing machine, TM2. Okay. So this was the input. So let's say we have a string like this. Zero, one, one. First, the tape head is here. So this is for Turing machine 2. So this is our finite control. So first job, what we were doing is that we were removing 0, replacing it with a blank. Okay. Then we were going at the end. So this was the end. We were finding 1 and replacing it with blank. Okay. Then after that, we were coming back to the start. This was the start. Replace it with blank. Then again go at the end here, replace this one with blank. Again, come at the beginning. So go back to the beginning. So this is now the beginning. Replace this with blank. Go at the end. This is the end. Find one. So one is there. Replace it with blank. Go again at the beginning. Now beginning will be this one. Okay. This one. And if at the beginning there is blank, so that means for every 0, there is corresponding 1. And in this case, we will accept this string. So this was our Turing machine. Now let's see, can this Turing machine recognize this particular string? Or let's say this particular string. So let me write only 2 or 3 here. So this string belongs to L1. So that means this TM2, it should accept this particular string. Okay. So let's see. So we have finite control. This is our input tape. What is the input? This is 0, 1, 0, 1. And here we have blank. Okay, these are blank, all blank. I won't write all here. So initially our tape head is here. So what is TM2 doing? So what is the job of TM2? First it will find 0, remove 0, replace it with blank. So this is blank. Then go to the end. Here is the end. Find 1. So 1 is there. Replace it with blank. Okay, that was the job. Then go to the initial position. So this is the initial position. Find 0, or there is replace 0 with blank. But here we don't have a 0. We have a 1. So it will immediately reject this string. This TM2 will reject this string. Okay. So by rejecting this string, it will say that this string does not belong to L1, but we know that this string belongs to L1. So we cannot use TM2 directly for this particular case as well, for L1 as well. Why? Because we have seen here that it won't work for all kinds of strings. It will work, TM2 will work for only those strings where the number of zeros and ones are equal, but first we should have zeros, then we should have ones. Okay, then only it will work. Fine. So we need a new Turing machine for TM for this language L1. So it is clearly TM2 cannot work for L1. Okay, so we need a new Turing machine for L1. So let's design a Turing machine for L1. So before designing a Turing machine, what will be the approach? The first is, so let's suppose this is the string. Okay, this is the string. Here number of zeros and number of ones are equal. The first is, so go to initial, symbol. Okay. The second is, so let's suppose we are going to the initial. Initial is 1. Okay. So, or in this case, initial is 0. So let me write it here. Blank. 0, 1, 0, 1. Okay, so go to initial symbol. So let's suppose this is our initial symbol. So this is 0. Okay. So if the initial symbol is 0, replace it with blank. Okay. So if initial symbol is 0, if it is 0, replace with blank and find 1. Now after this we will find 1. So 1 is here. Okay. So when we find 1, replace 1 with blank. Okay. So here we have 1. We will replace this 1 with blank. Okay. Now we are here. This is our initial. Again, initial is 0. So replace it with blank. Now find 1. Why is 1? Here. So replace it with blank. Now we have to again go to the initial symbol. But how do we know which one is the initial symbol? Whether this is the initial symbol or there is a possibility that there may be some symbol here also. Because for example, if it was, so let me give here, let me make you understand here. So this is 0, 0, 0, 1. Zero, zero, 1, 0. So first there was 0. I replaced it with blank. So let me write blank as B. Then 1, replace it with blank. Then we have to go to the initial step. So initial we can find. So it is, let's suppose 0, it is blank. Then we will find 1. So we will come here, replace it with blank. Now, how will it know whether this is the initial symbol or this is the initial symbol? So see, how were we determining which one is the initial symbol? So we were determining the initial symbol by finding it as left one. If the left one is blank, we were considering that as a initial symbol after that on the right hand side. But here there are two types of blanks. One blank is in between these two and another is this blank. So we won't be able to find the initial symbol. There is no possibility to find the initial symbol if we are using this approach. Which approach? Whenever we are finding the initial symbol, replace that initial symbol with blank. So for example, if initial symbol was 1, replace it with blank and then find 0 and replace it with blank. Then again go to the initial symbol. But here the problem with this approach is that since we are replacing with the blanks, so there may be some blanks in between the strings. And because of those in between blanks, we won't be able to find the initial symbol in the string. Okay. So instead of replacing with blank, replacing with blank, we will replace with a new symbol. Let's suppose X. Okay. So what I am saying, we will first go to the initial symbol. If initial symbol is 0, then what will we do? Replace 0 with X. Okay. Replace 0 with X. Fine. Or we can say replace 0 with blank. After replacing 0 with blank, find 1. So find 1, replace 1 with X. Okay. However, if initial symbol is 1, replace 1 with blank. Okay. Then find 0. replace 0 with x. So this is the second step. So for every 0, we are finding 1. And likewise, for every 1, we are finding 0. Now let's suppose if we have initial symbol 0, and if we are not able to find 1, so that means number of zeros is not equal to number of ones. Likewise, if initial symbol is 1 and we are not able to find the corresponding 0, then that means number of zeros is not equal to number of ones. So after doing this, go back to initial symbol. Okay. Go back to the initial symbol. Fine. Now, after going back to the initial symbol, repeat step 2 and 3. So we are going to repeat the step 2 and step 3 again and again. So how we are going to find the initial symbol? So can anyone say how we are going to find the initial symbol? The initial symbol we are going to find. So we can do one thing. So the best way to find the initial symbol is, or let me make it simple in a scenario like, so if initial symbol is 0, replace 0 with x. So instead of blank, let's write x here. So here also replace it with x. So go back to initial symbol. Okay, initial symbol will be always a symbol after blank. So this is a symbol after blank. Now the symbol after blank, so the possibility that it can be 0, 1 or x. So if it is x, we will ignore. So we will go the forward. Oh, okay, so let me write it here. So third step, go to initial symbol. So what will be the initial symbol? Symbol after blank. Okay. Then fourth is, if initial symbol is x, then find 0 or 1. Okay. So we have to find 0 or 1. If we first found 0, then we will find 1. So that means like this. We will then repeat the step second. So if initial symbol is 0, or we can say find 0. Okay. Or here we can say it is find 1. Find 0 or let me write the algorithm in clean words. So let me rub this and let me write it in clean words here, because there are some confusions. So let me first make you understand with the help of example what I am doing here. So this is our tape. So let's say it is 1 0 0 1 0 1. So what we are going, so this is blank, this is also blank at the end. So first we are here, so we have 1. Okay, so when 1 is there, we will replace it with x and then find 0. So 0 is here, we will replace it with x. Then we will go to the initial symbol. So the initial symbol will be this. So here we have x, so we will ignore x. Ignore x means we will go forward till we find either 0 or 1. Okay, so here also we have x, we will go forward. So what we have found? 0. 0, we will replace it with x and find 1. So find 1 means, so 1 is here, we will go x. Then again go to the initial symbol. Initial symbol will be again this. So now move forward. Move forward to find 0 or 1. So we have found 0, replace it with x. Okay. Now, since it is 0, find 1. So 1 is here, it is x. Now again go to the initial symbol. Initial is here. Okay. Again move forward. We are moving forward, ignoring x's. Now we have 1. Replace it with x. Now find 0. Is there any 0? So we will reach here, blank. Blank means that there is no symbol after this. So for 1, we are not able to find a 0. So that means this particular string will be rejected. Why? Because here the number of 1 is not equal to number of zeros. So what we are doing, what are the steps? Step 1 is find 0 or 1. Okay. Step 2 is replace 0. However, if it is 1, replace 0 with x. Okay. Then step 3 is find 1, or else if in step 2 we found 1, then find 0. Okay, find 1 and replace it with x. Okay, step 4 is go back to start. Step 5 is repeat step 1 to step. Okay. So now let me make a diagram, or let me make a graph here. So first is find 0 or 1. This is the start. So find 0 or 1. So that means if x is there, so we won't do anything with the x. We will replace x with x and move right. Okay. Now if we have found 0, replace 0 with x and move right. Move right means what should we do? Find. So we have found 0, now we have to find 1. However, if I found 1, first I have found 1, I will replace 1 with x and move right. Then I have to find 0. Okay. Find 1 means that I will keep on moving forward till I found a 1. Okay. So if it is x, I will ignore x and go to the right. Okay. If it is 0, I will ignore 0 and move right. However, if it is 1, I will replace 1 with x. Okay. Replace 1 with x and move left. Then what we have to do? So this step 3 is find 1 and replace it with x. Go back to start. Go to start. So how will we go to start? We will ignore everything. So if there is x, we will replace it with x and go left. If it is 0, we will replace it with 0 and go left. If it is 1, we will replace it with 1 and go left. However, if it is blank, so blank means that we have reached here. Okay, so blank means then we will go here, 1 position to the right. So that means that is the initial point position. So initial is this, find 0 or 1. So it will be here. So if it is blank, we will replace blank with blank and go right. So then repeat this. So this is repeat step 1 to 4. Likewise, find 0. If we have to find 0, so that means if there is x, we will ignore it. If there is 1, we will ignore it. However, if it is 0, we will replace 0 with x and move left. Then we have to again go to the start. So this is now here, find 0 or 1. If we are not able to find 0, neither 1. So neither there is 0 nor there is 1. So that means there are only x's. So for every 0, you have replaced that with 1. So there are equal number of zeros and ones. So that means I am trying to find 0 and 1, but that means I have completed all these. I have replaced everything by x. So everything by x means that for every 0 there is 1 1, and for every 1 there is 1 0. So that means when I have reached to the blank, blank means there is nothing after that. So if it is blank, so that means the number of ones are equal to number of zeros. Okay, number of ones is equal to number of zeros. So in that case, I will go to the Q accepted state. Okay, so this D here means that you can move in the left direction or right direction. It won't make any difference. Okay, now whatever the transitions are missing here, so whatever transitions are missing here, those transitions will lead to the reject state. So what are the transitions missing here? So can anyone say? So here we have one transition missing. Here there is one transition missing on blank. Okay, here also there is one transition missing on blank. So both these transitions, this one and this one, they will go to the Q reject state. Okay, so this is a Turing machine that will help you to determine, or we can say it will accept only those strings where the number of zeros is equal to number of ones, and it will reject all other strings. Fine. So this was another Turing machine that was designed, and the aim of this Turing machine was to determine the number of zeros is equal to number of ones. Okay. So now let's understand another problem. Okay, let's try to find out, let's try to design another Turing machine. That is, we will now understand example 3rd. Okay, that will be the last example related to designing Turing machines. Then I will give you some homeworks or some problems that for those problems you should design Turing machines on your own. So let's design another Turing machine for another problem. So let me rub this first. So let's see another example. For example, so we have design a Turing machine for incrementing a number. So we have a number. So let's say this is our number on the Turing machine input tape. So let's say number is 718. Okay. So here we have blank, and this side also we have blank. We want to increment this number. Increment this number means the number on the tape after incrementing should be 719. Okay. This should be a number. And if I want to increment this, so after incrementing, it will be, so the value will be 720. So we want to increment a number. The number is available on an input tape, and we want to increment a number using a Turing machine. So let's see what are the steps. So first is, so we will go, so initially we will be here at the beginning of a number. We will go to the end of a number at the end. So the first part is go to end. Okay. Go to end means that we have to go to the right direction, one after the another, till we reach the blank. And when we reach the blank, we will move one place left. So that means we will be at the end. Okay. So go to end of a number. Okay. Second point. What is the second point? The second point is update this number, this last number. Increase it by 1. Okay. So increase it by 1. So increase it by 1. What does that mean? Increase it by 1. Increase it by 1 means that if it is 0, make it 1. If it is 1, make it 2. If it is 2, make it 3. Dash, dash, dash. If it is 8, make it 9. However, if it is 9, so if it is 9, what we should do? We should make it 0. Okay, make it 0 and increment it is previous one. For example, here it was 9, so we make it 0 and increment it is previous one. What was the previous one? 1. Make it 2. Okay, so increment it is previous. Increment it is previous. So increment, what is the meaning of increment? If it is 0, replace with 1. If it is 1, replace with 2. If it is 2, replace with 3. Now, for example, if this one is also 9, so let's say this one was also 9. Okay, or let me do one thing. So let's say the number is like this. So 9, 9, 9, 9. Okay. So first we will go to the end. So that means we will come here. Now move one left. So we will come here. So it is 9. So we will replace 9 with 0. Move left. Move left, come here. Means increment this. So we will replace it with 0. Move left. Increment this. Replace it with 0. Move left. Increment this. Replace it with 0. Move left. So move left is now blank. So if it is blank, replace blank with 1. So that is the job. So increase it by 1. So after increasing by 1, incrementing by 1. So this is replacing 9 by 0. So here we were having 4 9s. So it is possible that there may be 10 9s. So this is also called a wrapping nines. Okay, wrapping nines. Increment it as previous one. Then what is the third part? The third part is go to beginning. So this is not required, but we should go to the beginning. Okay, fine. So let me design a Turing machine now. So initially we are at the start. Okay, so this is our start. So what is the name of this state? So this state, the job of this state is, what is the first step? Go to end. So let's name it go to end. So how we are going to end? So whatever comes, so if it is 0, replace it with 0 and move right. If it is 1, replace it with 1, move right. Dash, dash, dash. If it is 9, replace it with 9 and move right. So end means we will encounter a blank. So if it is blank, replace it with blank and move left. So it is like here. So we are going right, right, right. We reach it here. So here it is blank. So we will move one position left. So that means we are at the end. Okay. So we are at the end. So now when we have reached to the end, what is the job? Wrap 9s. So we have to wrap 9s. So whatever 9 is there, so if it is 9, replace it with 0 and go to the previous one. Previous one means left. Okay, go to the left. So if the left is not 9, so for example, if it is 1 or something else, 2, 3, 4, 5, 6, 7, 8, up to 8. Okay, if it is anything up to 8, we will increment it by 1. However, if it is 9, again it is 9. So let's say it is again 9, then again we will wrap it with 0. Okay, we will replace it with 0 and move left. Then we have to increment by 1. Increment by 1, that is the previous one. So if it is 0, replace it with 1 and move left. If it is 1, replace it with 2, move left. Likewise, if it is 8, replace it with 8 and move, replace it with 9 and move left. So that means up to this point, this state, when I am in this state, so I have incremented the number. Okay. And also you have to remember, if it is blank, replace it with 1 and move left. Okay. So this blank will be this case when all are 9s. Okay, then we have to replace this blank by 1. Right. So now we are here. Now we have to go back to home. Go back to home. So how we are going back to home? We will go back to home, whatever is there. For example, if it is 0, replace with 0, go left. If it is 1, replace with 1, move left. If it is 9, replace with 9 and move left. We are going to the left. So we are moving to the home. That means we will reach to the blank symbol. So at the blank symbol, we will move one step to the right, and that means we have completed the increment of a number. So if it is blank, we will replace the blank with blank, okay, and move one position to the right. And this final state will be our Q accept. Q accept means we have completed the procedure. So this is the Turing machine for incrementing a number. So these are some of the Turing machines, some of the examples where we have understood how we can design the Turing machines. Likewise, we can have a Turing machine, so we can design a Turing machine to decrement a number. Decrement a number. Okay, design a Turing machine to decrement a number. So this will be your homework. So you have to design a Turing machine to decrement a number. So let's name this Turing machine as Turing machine I. I means Turing machine for incrementing. So you have to design a TMD, Turing machine for decrementing a number. So these are two Turing machines. So this is your homework. The other portion is that will be your homework is that you have to, another homework is design Turing machine for L is equal to A raised power n, B raised power n, C raised power n. Design a Turing machine for this particular language. This is also your homework. The other thing that you have to make is another homework for you is that you have to design a Turing machine for L is equal to W dot WR such that W belongs to A, comma B star. This is also your homework. Another homework for you is to design a Turing machine to sum two numbers. So the two numbers will be given, for example, 6 and 3. Okay, so you have to add these two numbers. Okay, for example, this is your input tape. So on input tape, there will be like this. For example, these are 3 places, and then we will have a blank. These are 2 places. So let's keep only 3-digit number and 2-digit number. Okay, so here is one number. So let's suppose it is 6. So let's write it 006, and this is 303. Okay, so you have to add these two numbers. The final answer should be at this location, it should be 009. Okay, so we don't care about the other side, these cells. Whatever is there, we don't care. But here it should be 009. Okay, so design a Turing machine to sum two numbers. I will give you an idea how to add two numbers. So what you have to do, you have already designed Turing machine for incrementing and Turing machine for decrementing. So this is your homework. You will design a Turing machine to increment and Turing machine to decrement. Then what will you do? You will use these two Turing machines to design this Turing machine to sum two numbers. How? What you are going to do, you will be first here, you will go here at this location, decrement it. Okay, so for decrementing, you will use which Turing machine? TMD. So decrement it by 1. Okay, go here. So after decrementing, it will be 2. Now come back here, increment this by 1. So you will use which machine? Turing machine for increment. So 6 will become 7. Then again go here, use decrementing. So it will become 1. Come here, use Turing machine for incrementing. It will become 8. Then decrement this again, Turing machine decrement. It will become 0. Increment this using TMI. It will become 9. Now come back here. So now here it is 0. So when this is 0, that means you have to stop. When this is 0, stop. So, and this will be your answer, 9. So you will design this Turing machine to sum two numbers using Turing machine for incrementing and Turing machine for decrementing. So you can see here, these are our two subroutines, subroutine 1 and this is subroutine 2. So we have used these two subroutines to design this particular Turing machine. Fine. So your job is to not only understand how to design Turing machines, you should also try out these 4 problems that I have given here, to try out to make Turing machines for these problems that will help you to understand how to design larger Turing machines. Okay. So let me stop here. Let's stop this particular lecture here. From the next lecture, we will start discussing about the Turing machines, how powerful they are. So we can say the power of a Turing machine. Okay, and we will also see it as a relation with a real computer. So these two topics we will be discussing in our next lecture, that is lecture number 30. So in this particular lecture, lecture number 29, we have completed the designing of Turing machines. We have discussed 3 problems here, and I have also given you 4 problems as a homework to design Turing machines on your own. So let's meet in the next lecture where we will be discussing the power of a Turing machine and a relation of a Turing machine with a real computer. So let's meet in lecture number 30. Till then, goodbye.